is Wael Ben Amara, and today I'm going to be presenting a paper entitled A Comparison of Distributed Machine Learning Platforms by the authors Qtsong and others. So the motivation for the choice of this paper is essentially the project for this course. So I needed to learn about architectures that allow me to run ML-based applications on top of a distributed environment. Also, data is getting very voluminous, so designing machine learning applications that train models using um, this big amount of data has become a really big challenge. Also, I had the interest of exploring the pros and cons of each framework in order to be able to make an appropriate choice about the architecture of the project. So, moving on to the project architecture. So, this slide has nothing to do with the paper presentation, but we are displaying it just to show that our project has actually the need to be deployed on top of a distributed systems environment. So as you can see, it has a bunch of modules that are connected together, and each type of module needs to be run on an independent node, and not a singular module needs to perform ML based operations. So this paper is very relevant for our project and will help us determine which framework we can use. Okay, so the paper is actually a survey paper. So basically in survey papers we compare between two or more things, for example, frameworks, algorithms, products, and a bunch of other kind of stuff. So in this paper, we are actually comparing frameworks slash architectures. So the frameworks we will be comparing are Spark, TensorFlow, PMLS, which stands for Parallel Machine Learning Systems, and also MXNet. Also, we would like to analyze the communication protocols between the components of each framework and explore the bottlenecks of each system. We would like to also determine the fault tolerance and the ease of development of each approach. Okay, let's start by Spark. Spark is actually now considered as the successor of Hadoop, as Hadoop is considered to have reached its end of life cycle. So the community says that Spark performs better when it comes to MapReduce, as it avoids to write a lot of intermediate states on the disk. So the permanent communication back and forth with the disk is eliminated using Spark, using the resilient distributed dataset. So it basically creates an execution plan by a directed acyclic graph. So this is how it actually works. So basically the processing of an RDD, which means the resilient dataset, is performed through the drivers and executors. The drivers create the Spark context. It defines the executors and the task to be performed. So a physical plan is then created, and then the cluster manager takes care of scheduling how each executor will work. The cluster manager uses a directed acyclic graph to schedule the tasks, and each vertex represents an RDD, and each edge from vertex A to vertex B represents an operation made on A in order to obtain B. So in order to run Spark for machine learning, we will actually need an intermediate library called MLlib, because Spark was not initially designed to perform ML operations. So MLlib is basically an interface that allows us to use the Spark architecture in order to make machine learning applications. So basically, the model parameters are stored in the driver, and the workers communicate with the driver to update the parameters. But sometimes the model is very big, um, and if the model is very big, sometimes we cannot store it on a single machine. So we will so in our case, in Spark's case, we will need to store it on an RDD, which actually reduces the speed of the training, and this can be an inconvenient when it comes to very large scale machine learning projects. Moving on to PMLS, which stands for Parallel Machine Learning System. So basically, uh, the parameter server is implemented in a distributed fashion, and the parameters are actually stored across these tables. So remind that in the case of Spark, uh, if the project is very big, we will create an RDD in order to store the model parameters. But in this case, we are actually storing the parameters in a data structure called tables in each of the nodes. So the worker performs computation on a partitioned dataset, and each worker may contain multiple threads. And here we are using the stallness synchronous parallel instead of the bulk synchronous parallel. So what this means is that the algorithm may actually not uh, keep waiting for the other threads to complete. For example, if we are working on a certain thread and we need to wait for another thread to complete because it will update the model parameters, what we can do instead is use the previous iterations and load the model parameters from previous iterations in order to complete a certain thread that could be computed fastly. So this will make us gain a lot of time, but actually will make us lose in consistency. But the good thing in PMLS is that it allows us to choose between speed and consistency. So it gives the freedom to the user to define whether he likes consistency over speed or the opposite. So moving on to the famous TensorFlow. So TensorFlow is basically built from three components. So the first component is the client. It's the one that we usually use. Um, it's basically the interface from which we communicate with, for example, from Python. So this is where actually the user defines a computational graph for for the execution. We can, when we are, for example, coding with Python, we are not actually explicitly doing that, but what happens is that um, the code we are writing will translate to a computational graph, and then we have the master. It is the one responsible of scheduling the job one over one or more workers, and the worker is the component that will handle the request and execute all the things in the computational graph. So TensorFlow actually has support for subgraph execution. What this means is that um, each graph can be decomposed into subgraphs, and we can execute each subgraph independently from the other. So this actually allows the parallelism process. So basically, each client builds a graph containing the parameters and the compute intensive part of the integral graph. And we have two modes, so the synchronous mode and the asynchronous mode. And if the mode is synchronous, all the replicas read the same values from the parameters. And if the mode is asynchronous, so each replica will have its own parameters. Finally, we go to MXNet. It is very similar to TensorFlow. Um, it allows cyclic computation graphs with mutable states, and exactly like TensorFlow, it provides good data parallelism on GPU and CPU. So the evaluation, in order to do the evaluation, the authors considered the logistical regression. So they gathered 10,000 data entries with 10,000 features for each data entry. So this resulted in having 750 megabytes of data. The frameworks considered in this experiment are PMLS, MXNet, TensorFlow, and Spark. And this resulted in having PMLS and MXNet to be the fastest, followed by Spark, and then followed by TensorFlow. So the question that we should ask is why are they faster? So the response uh, provided by the authors was that the implementation of the fastest algorithm was in C++, and while others were using the Java virtual machine, and the C++ actually allows people to uh, have very efficient and very tight programs, while using TensorFlow, there is a lot of abstractions for the users. So, for example, if you are using Python, um, in order to translate your code into a computational graph, that would take some time. In conclusion, the data flow model actually fails to scale due to lack of support for mutable state and fast iteration. So the parameter server came to solve the issue, and the researchers are considering converting the data flow systems into systems that are compatible with parameter server models, and this is by allowing cyclic execution graph to with mutable state. Yeah, so that's it. Thank you for following us, and we hope you have enjoyed our presentation.